Can you see my screen?
Yes, the screen is visible to us. It is in full screen now.
Yes. So I can start now, right?
Yes, you can start.
Okay, so today's topic is on DC fast charging and optimization of EV charging using machine learning. Now, today's world is moving towards EVs. So one of the major reason that we are moving toward EV is not the major reason that we are try to cut down the carbon emission and all. The main reason is to use renewable energy for transportation purpose. Okay, that is only feasible when you use that energy as electrical energy, store it, and then use it for other purposes like the electric vehicle, where that electric vehicle is going to replace the IC engine based internal combustion engine based vehicle very soon, and it is already been started. Okay, the shift is moving, so the shift is towards EV, but the few problem or few challenges that we are facing and we are going to face in near future is, one is the battery technology, because when it is EV electric vehicle, the only source of energy is the battery. So battery technology has to be improved significantly. That is one thing, one challenge. Another challenge is, we are going to charge the batteries from the conventional grid, and grid has to support that amount of power that we are going to consume from the grid. Now, as number of EVs are increasing, the load on the grid is increasing. Also, the EV load is not that small load. Number of EVs are increasing, load on the grid is increasing, and there is a shift of peak load demand on the grid to the higher side. That we'll see. Now, how it is going to affect our grid as we are increasing load day by day, that we'll see. And also how the machine learning, we can use machine learning to optimize or to help the grid uh, to meet the demand in such scenarios. Now, when it is EV, the one of the important point to be mentioned here is, when somebody, a layman, he or she is not an electrical engineer, not an automobile engineer or something, he or she is going to buy a car. Now he or she is going to compare that vehicle with the other vehicle, existing conventional vehicle. When we are talking about, let's say, IC engine based vehicle, it is going to, you buy that vehicle, and when you need energy, or in this case it is a liquid fuel, which is petrol or maybe diesel or maybe CNG, whatever it is, go to the gas station, go to the petrol station, and then immediately fill it. If you cut down the queue that you have to be in, then refueling of the vehicle will take at the max 3 to 4 minutes. In case of electric vehicle, this is not the case. Now if somebody is going to buy an electric vehicle, and if you tell them that, okay, you are buying this and you have to charge it for 11 hours, so definitely it is a discouraging thing for a customer to buy that electric vehicle. So in order to get an experience similar to that, what we do is we come up with DC fast charging. What is DC fast charging? Now let's not talk about DC, let's talk about fast charging. In fast charging, what we do is, it's like you have a water tank, and in that water tank you have three inlets. One is small, another one is medium, another one is large. When there is a small inlet, the filling of the water discharge, water inlet from that small inlet will be, rate will be low, and the tank will take time to fill it. When it is when you use the large inlet, the water inlet, the amount of water coming per liter is coming is high, and the tank will fill immediate, means tank will fill comparatively faster than the previous case. Here also, in case of battery, what we do is uh, we charge the EV battery at very high current, so that the charge accumulation to the EV battery becomes faster, so that the refueling experience that you are going to get similar. I am not saying same, similar means if there it was 2 to 3 minutes, here it will take 20 to 30 minutes. At least that people can bear, comparing the advantages that you are going to get with the EVs. So that is called DC fast charging. Now in DC fast charging, the the problem is you have to disperse a huge amount of power to the electric vehicle, huge amount of power to the electric vehicle within a short span of time. When the time is small, during that period, the source is utility grid. You will see that what is utility grid? The three-phase grid that is coming to your the coming to your locality, from where the single phase supply you are taking to your home. That is three-phase utility grid. That voltage level is 400 volt in India and some other countries as well. So from there you are taking that huge amount of power. If you don't consider power, if you talk about the current, the huge amount of current that you are going to take from the grid, it is your demand that you are going to take. Now who is supplying that power? That utility company has to take care of it. If the utility company is allowing you that yes you can do it, then utility company has to take care of this, that this load is going to this much amount of huge power during this period. So in order to make that utility company aware of it in beforehand, there is a forecasting technique that we are going to employ, and that forecasting technique will be employed using machine learning algorithm. So here we have DC fast charging, and then forecasting we have using machine learning. So when we have the forecasting beforehand, then it is for the utility company to supply that amount of power during that period, so that the stability of the grid can be maintained. That is a huge term, stability. That stability of the grid could be, the stability problem in the grid could be some various reasons, but one reason could be, it is like a human being is working, and the human being is overloaded, and then again you are loading that human being. So at certain amount of time, after a certain amount of time, there will be a failure. It is similar kind. It is grid is supplying power, the conventional grid is supplying power to the household, the industries and all, and suddenly you come up with 2 and 3 EVs, and you are asking for huge amount of power in DC fast charging station, and grid has to cater that load, because the grid has committed that okay, I will supply that amount of power. So that is fine, but if grid is having a beforehand information that this is going to happen, so definitely it will be useful for the utility company to supply this power at that certain amount of time. So with this introduction, let me start with the stop. So in order to understand this DC fast charging and all, some basic thing that I want to talk about the battery and all, that will come one by one. So I'm skipping this. Okay. Now I am on slide 3. Is it visible everywhere?
Sir, it is visual, sir.
Visible. Okay, fine. Okay. Now there is a term called C rate. Okay, so every battery comes with a C rate. C rate. What is C rate? It gives the amount of charging discharging current. A battery is there. So battery you are charging at, let's say, 0.5 C. So with that information, you can have two information. One is at what current you are charging the battery, and how much time the battery is going to take to fully charge. Now, why we always talk about current going to a battery? Because battery is an electrochemical device. In contrast to the example I have considered, that a tank is filling water to a tank, that's fine. But here, since battery is an electrochemical device, when you are charging a battery at high current, there is an internal resistance of a battery. Internal resistance is not like rheostats that we have. It is internal chemistry that is giving some resistance to the battery, internal resistance to the battery. When you are charging the battery at, let's say, low current, that I square R loss to that resistance is low, so battery is fine. When you are doing DC fast charging, you are doing at very high current rate, so it becomes I square R loss becomes high. Because of that, that heat is accumulated in the battery, and battery is getting heated. Because of that, the battery chemistry is deteriorating, so the health of the battery is in stake. So battery charge discharge rates controlled by the C rates, current at which battery is charged and discharged. So therefore, as I told that if it is high current, it is harmful for the battery, but we'll see at what condition we can do that. But so when we know about C rate, so we can know that okay, this much amount of current is going to the battery. How we can know that? Let's say, so battery capacity is leveled at 1 C rate. That means what? Let's say there is a 10 ampere hour battery. Okay, 10 ampere hour, 12 ampere hour battery. Okay, so that means at 1 C, if we say that battery is charged at 1 C, so it is 10 ampere is going to the battery, and 10 ampere going to the battery or taking out of the battery. So when the battery is supplying 1 C current, that means 10 ampere for this particular example, 1 C current it is delivering, that means 10 ampere, then it will last for 1 hour. This is the convention, 1 hour. So if we discharge at 0.5 C, it will provide 5 ampere, and time will become 2 hours, because 10 ampere hours means 5 into 2, it becomes 10. So similarly, the time we can calculate, time and current we can calculate, but time is the rough estimation of the time, because when you are charging more, when you are discharging battery at more current, there will be loss. So the amount of time for which the battery is going to, the duration for which the battery is going to supply current will get reduced. It is not exactly 30 minutes as in the case. It will be, let's say, 25 minutes, depending upon the type of battery. So as I told, the C rating, if somebody says that at this C it is battery charging or discharging, you can know the current as well as you can know the time. So at higher C rate, energy is lost, lowering the capacity by 5% or more. That I told already mentioned. Okay. Now let's do some example. So let's say there is a battery of 23 milliampere hour battery is there. Okay. Now you are taking current at 0.5 C rate. So at 0.5 C rate means 1 C means 2300 milliampere hour means it is 2.3 ampere hour battery. So 2.3 ampere is the 1 C. So if it is 0.5 C, it will be half, which is 1.15 ampere current. So time that battery can supply is around 2 hours or 120 minutes. Similarly, if it is 2 C rate, then it is 30 minutes or 0.5 hours. If it is 30 C rate, it is 2 minutes or something like that. So this is how we C rate is going to affect the battery time, the discharge time, and also it defines the current. Okay, why we are talking about C rate, we'll understand in subsequent slides. Now here we have an example, a battery example. Okay, lithium ion battery from Panasonic. So this is a cell, battery cell. Okay, so the battery ampere hour here is given as 1950 milliampere hour. So its 1 C rate will be 1.95 ampere or around 2 ampere. So you can see here rated capacity minimum is 1950 milliampere, and its typical is 2050 milliampere hour. So nominal voltage is 3.6 volt, and there is a charging. There is a technique called, I don't know how many of you know this. There is a charging technique called CC and CV. You can see here. So you can see here CC and CV. CC and CV means, CC means constant current and CV means constant voltage. So what it does, It's again we take the example of water tank. So let's say water tank is completely empty and you want to fill the water tank. Now what you do is you start filling the tank at certain rate and you fix that rate, that is you supply current to the supply water to the tank. Now if you continue with it, then at let's say you 20 liter per minute you are filling the water tank. Now if you keep it for the entire time, so there will be a time after which the tank will be overflow, water overflow will happen. Now in order to avoid that, what you can do is, let's say you are monitoring the water level, and when it is 80% water level has reached, now you change the flow rate and you subsequently reducing the flow rate so that overflow doesn't happen. Okay, so the same technique that we use in battery charging, SCC and CV, constant current. So initially we charge at constant current, keeping the current constant up to let's say 80% SOC. SOC means state of charge of the battery. Now when it is 80% SOC is reached, then it move into constant voltage. We keep the voltage across the battery constant and on little bit higher side, so that current flows from the source to the battery and battery keeps charging, and battery current going to the charging current going to the battery subsequently reduces. So here you can see that, here you can see the charging current is given as 1.37 ampere. Okay, so what is the C rate? You can calculate from this. Okay, so this is the charge characteristics. As I was mentioning, that constant current and constant voltage. You can see here the green one is the current profile, that is charging current profile, that is the current that is delivered to the battery, current delivered to the battery. So till 60 minutes, you can see here the green line is constant. So current is constant. So how much is the current? It is mentioned that 0.7 C, maximum 0.7 C there. So charging, as I was mentioning, why it is important to mention about C rating. So C rating is the battery data sheet will tell you what is the best C rate for the battery. So here it is, they are saying that the constant current charging is done at 0.7 C, and then when after 60 minutes it is constant voltage charging. Okay, so this is how the constant current and constant voltage charging profile we use. This is because, let's say you are doing constant voltage charging. If it is constant voltage charging, so as the battery keeps on charging, then battery voltage is elevating. So when battery voltage is elevating, then the difference between the source voltage and battery voltage is reducing, and therefore the current supply to the batteries is reducing. So the charging time will be huge. In order to reduce that, what we do is quick charging with constant current charging till 80% SOC, and after that we maintain the voltage so that overcharging doesn't happen and the battery reaches the rated capacity. So that is why it's constant current and constant voltage charging profile we do. Okay, now this C rating will be defined in case of DC fast charging. We'll see. Okay, another thing you can see here in this discharge characteristics. So as I was mentioning that there is an internal resistance to every battery. So as you see, there are different color lines are there. So point C, when discharge is in constant current discharge, you can see here when current is more, you can see here 10 ampere. This day they are mentioning 0.2 C, 0.5 C, 0.1 C, 2 C, and then 10 ampere. So you can see here there is a significant difference in voltage. This is a voltage, this is y-axis is voltage. There is a significant drop in voltage. This drop in voltage is due to the IR drop, the internal resistance and the current supplied by the battery, that drop, and this is the voltage that you are going to get at the battery terminals. Okay, now this is just you need to know this, because every company They will mention that they are going to use lithium ion battery, but they will not mention what type of lithium ion battery they are going to use. Okay, so there are two major type of lithium ion battery that is useful for electric vehicle. One is NMC and NMC, another one NCA. NMC is the lithium nickel manganese cobalt. It's a popular type lithium ion battery, with a high energy and power density. Charging profile is performance is good, and there are more recyclable material that is used in this battery type, and it is relatively safe, because when you are using an electric vehicle, it should be safe. It is not like you are using it and then something happens, because battery is very dangerous. There are cases reported, like in news, that regularly comes, that this when you are parking a electric scooter outside, because of extreme heat, that battery catches fire, and all those incidents are regularly reporting. Okay, so it should be safe. The battery should be safe. NMC is most common in EV model due to its good range and charging performance. Companies using Tesla, Volvo and BMW, they are using NMC batteries. Then we have lithium nickel cobalt aluminum oxide NCA battery. It is high energy density than NMC batteries, and Audi is using this NCA lithium ion battery. Now let's talk about what is DC fast charging and how it looks like in commercial vehicle that is available in the daily life. So Nissan Leaf is a car which is very popular in USA. So I have taken this data. So in March 2022, that data. So its range is 235 kilometer, and battery, and this is 166 watt hour per kilometer that is used. So usable battery capacity is 39 kilowatt hour, and here battery type is lithium ion. Okay, nominal battery voltage is 350 volt. Okay, so can anybody tell me why it is 350 volt and not why it is voltage level is on higher side and not on lower side? So if you know, it's fine. Otherwise you can think on why going for higher voltage, because it is a car. Okay, so why we are going for higher voltage, rather it is better to have it on lower voltage. Okay, now they provide a home charging. They provide a home charger whose power level is 3.6 kilowatt AC. From AC it will take, and it takes around 13 hours. When you are at home, okay, no urgency is there, then you bring that car to home and put it in charge overnight. Okay, let's say you started at 8 and morning 8 or 9 it will be fully charged. You see the timing of charging. Okay, the night time, because let's say you are taking that car to your office, the whole day you are in office, and then you come back to home at, let's say, 6 or 7 p.m., and then you put the vehicle on charge maybe at 7:30 or 8. Now this time is crucial. Why? Because when you start charging this vehicle, okay, that time already the grid is overloaded with the night loads. Okay, various lighting loads, TVs, everything is working. Okay, at that time you are putting the vehicle on charge. Okay, let's say I am putting the vehicle on charge. What is the harm? Like you, there are several people are going to charge the vehicle from the grid, and that is going to create a peak overload on the grid. So you are loading the grid during that time, 8 to maybe from starting from 8 p.m. you are loading the grid. So this you have to take care. The grid has to take care of it. Okay, but here you see the charging power level is only 3.6 kilowatt, because it is home charger. There is a limitation, limitation of power, how much you are going to take from the single phase supply. So they are not going to allow you the huge amount of power. There is a limitation. If you, yes, you can take it, but if you want to take more than this, then what you have to do is you have to take three phase power. Okay, the tariff is different, the chargings are different. Okay, so you take three phase, and then from there you charge your vehicle at a high power level. But that is not currently that is not the state of art. What you have single phase supply. So from single phase supply, using this slow charger, which is 3.6 kilowatt, you charge your vehicle, and it is going to take 13 hours. This may not be a regular affair. Maybe once in a week you have to charge, or twice in a week you have to charge, but you have to do it. Then they are providing DC fast charging. So here you see 46 kilowatt. You see the difference. It is more than 10 times the power. Here it is, when it is DC fast charging, power is more than 10 times. And also, since it is going to take from the three phase grid, so we can increase this power. It is possible to increase this power from 2.6 to 3.6 to 4.6. And here you can see there is a significant difference in time. Here it is taking only 43 minutes to charge your vehicle, and charging speed is 230 kilometer per hour. In home charger it is 18 kilometer per hour. Here it is 230 kilometer per hour. So you have to wait for, let's say, 40 to 45 minutes, and your vehicle is charged. So that is why the DC fast charging is preferred from the customer point of view. Okay, from grid point of view, you have to supply this amount of power for 43 minutes, and if you have, let's say, 10 such vehicle you are going to charge from the utility grid, it is 460 kilowatt, which is almost 0.5 megawatt. The grid has to supply for that 40 minutes. Okay, so this is how. And another important point is, this is not any higher level grid, medium voltage grid, or higher voltage grid. It is that power you have to supply from the utility grid at distribution level, 400 volt grid itself. Okay, now here you see what is the C rating difference. So when it is home charger, the C rating of the battery, that at which the battery is charging, it is 9 ampere, which is almost 0.09 C. Whereas when it is DC fast charging, it is almost 131 ampere, and it is 1.2 C. So it is generally the home chargers we charge at very low C rate. Okay, 0.05, 0.02, 0.08, something like this. And the fast charging we do at 1C rate. So when it is 1C rate, that 1C rate charging of a battery is not recommended for a longer period. So here it is, the battery is taking only for 40 to 45 minutes. That's fine. But let's say your vehicle battery is completely discharged. So in order to charge that vehicle battery, it will take much time, and that for that duration, that DC fast charging is not recommended. If it is top-up charging, for top-up charging, let's say your SOC level has gone down to 60%, and from 60%, so let's say 80 or 85% you want to charge it, yes, DC fast charging is recommended. But fully discharged battery, and that too on regular basis, that every time you are doing DC fast charging, is not at all recommended. It is going to deteriorate the battery life. Then I have taken another example, other bike, where we have 2.4 kilowatt hour usable battery capacity. This is a e-scooter that is readily available in India as well. So lithium ion battery, 4 batteries are connected in series, 12 volt battery, 50 ampere hour. So 51.1 volt is the battery nominal voltage. So here they provide a third dot, which is 60 volt charger to 60 volt 12 ampere. So here power level is low, 720 watt AC, and it takes almost 4 hour 30 minutes, and 80% charging, and 100% charging more than 15 hours, more than 5 hours. When it is DC fast charging, they have other grid where the charging power level is 3.3 kilowatt. DC fast charging, it takes 50 minutes to charge 100%. Okay, here also you can see here the home charging current level is 0.2 C, whereas DC fast charging, the battery is taking 1.4 C, 1.4 C. So when it is around 1 C, 1.4 C, 1.2 C, it is DC fast charging, and battery is taking huge amount of current. Okay, now this is fine. So we have scooters, we have cars, but major players in India, the electric vehicle, are the e-rickshaws. Okay, there are huge amount of e-rickshaws are playing in various cities that I have experienced. So these e-rickshaws are used for business purpose. So why I'm telling this a difference between this business purpose and this the people are using for at home for their personal usage. The difference is when it is for business purpose, what they do is they go for business maybe early in the morning, maybe 6 or 7 a.m. and they come back by 6 p.m. or maybe 9 p.m. And when they are coming back, their battery is completely discharged, so they have to charge it. So every day there, as I was mentioning, that maybe once in a week, twice in a week we are charging the vehicle. Here when it is e-rickshaw, since it is used for business purpose, they are completely use the battery. So every time they are coming back home and they are using, they're charging it. So there are number of e-rickshaw players, and they are using their slow chargers, that is available with their vehicle, and they are charging every night. And there are huge number of e-rickshaws are playing, and every time, so these e-rickshaws are, there is no in India, there is, it is coming up, the renewable energy based charging stations and charging infrastructures are coming, but currently our grid is supported by coal based power plants, and we are supplying power from that conventional grid. Now what is the problem with this? The problem is, when it is coal based power plant, the efficiency of coal based power plants are 40 to 50%. Okay, when we are talking about, when we are talking about improving efficiency and all, and then we are charging our electric vehicle from conventional grid, where the grid is supported by coal based power plant, then it is not a success. Success is when we are using this electric vehicle and the power we are utilizing from renewables, then the success of EV will come into picture. So then we have, so there are e-rickshaw. What is there in e-rickshaw? We have similar four 12-volt battery, 80 to 120 ampere hour, and they are coming back home. There is no fast charging or charging infrastructure. Significant improvement in charging infrastructure is not there now. So they are coming back home, 8 to 10 hours they are charging. I personally talk to them. They are saying this. They are saying they have chargers, and in that charger, they see how they are trained. Okay, they have chargers. They told that they have charger with different current tapping, and they always keep the current level going to the battery at lower side, because you can change, there is a tapping, you can change it manually, you can change the current level going to the battery, they manually can change it, but they are saying that they don't do that because it heats up the battery. That is one thing. Another thing is, when it is e-rickshaw, since there is extensive use of battery, and those batteries are lead acid batteries for the current state of art, so it lasts long for 8 months to 14 months. The battery lasts long for 8 to 14 months, and the amount of money they have to spend in one year, 40,000. Okay, the amount of and that too, so battery is getting deteriorated very soon. So battery is not, every year you have to spend 40,000 on battery, and when you're buying new battery, if you give the old battery, they get some incentive of maybe 10 to 12,000. So you have to spend a good amount of money for this battery. So there is a scope of improvement in battery technology for e-rickshaw. There is a scope of improvement in charging technique to the e-rickshaw, and there is a scope to improve the battery life that they are using it. There are companies, they are trying to build the rapid chargers. So these examples are given in Bangladesh also. There are many e-rickshaws, so they are also trying to install the solar based charging station for these e-rickshaws. Okay, now here you see here, three phase grid connected 15 kilowatt Bharat DC fast chargers are there, but they are three phase grid connected charger. When it is grid connected charger, definitely, as I mentioned those things, that what are the challenges that we face, that will come into picture. So now DC fast charging provides refueling experience similar to, I should not say similar, but yes, very close to this refueling experience of diesel or petrol based vehicle. DC fast charging of these discharge batteries shorten the battery life. Yes, you can do it. It is up to your wish. They will do it. They will do it for deep discharge battery, but definitely their battery life. Now what we do is, I have a mobile. Okay, so there was a charger. There is a compatible charger provided by the company, and I was using it. Somehow I lost that charger. Now I bought a charger of higher power rating, and when I charging it, the battery, the mobile is getting heated. Okay, so this is the reason the battery is now charging at higher current. Mobile battery is charging at higher current, and battery is getting heated, means the lifetime of the battery is getting deteriorated. Okay, we are shorting the battery life. So if you are doing this on regular basis, okay, you are doing something harmful to your battery, whatever battery, whether it is mobile battery, whether it is e-scooter battery, whether it is e-rickshaw battery, whatever it is, you are deteriorating the battery life. So regular DC fast charging harmful and suggested not to use on regular basis. Okay, you are doing it, let's say, for once in a month, once in a week, or maybe twice in 2 weeks or something like that. So it's fine. It may be, that depends actually. I should not say fine this term, but it depends on the battery. What is, because when you started using the vehicle, the SOH of the battery is high. When you are subsequently using it, the battery SOH is deteriorating depending on the current state of health. SOH means state of health of the battery. This DC fast charging, whether it is recommended or not recommended, that can be decided. DC fast charging recommended for smaller duration and to boost the battery SOC and not full discharge of deep discharge batteries. Okay, let's say take an example. Now this e-rickshaw I was talking about. Let's say if we have a charging station, DC fast charging station. Now there maybe one or two e-rickshaw. Let's say they are playing and they found that their battery capacity has come down. Now if we do, they have to go home, they have to use that slow charger, and then again they charge, and it will take maybe 2 to 3 hours, and again they will come back. So they are losing 3 hours business, 2 to 3 business hours. So instead of that, let's say you provide an opportunity for that e-rickshaw player, that okay, we have a fast charging station, you come here, it will take only half an hour to refuel it, and then you go for the business, for your business. That will be helpful, that person, that will be helpful, that e-rickshaw owner. Okay, so this is how the DC fast charging is going to help that person. But yes, definitely on emergency basis, on top up basis, and not on regular basis. Okay, now since, as I was talking about, DC fast charging amount of energy is huge that you have to supply. So the infrastructure that we have to build, or the converters that we have to build, is large, and there are different configurations. Just I have given some example taken from this paper. This is so battery is there, so you can see here battery is there, and then we have parallel converters, because as you have seen that when it is DC fast charging, you have to supply huge amount of current, so that can be done using paralleling. So summation of currents, paralleling of the converters. Okay, here also paralleling of the converters, and this grid is nothing but the utility grid using a low frequency transformer. And here, so two solutions are there. One is using low frequency transformer, this is using high frequency transformer. What is the difference between these two? When it is low frequency transformer, let's say you are in a very busy city. Okay, it's a very old city, it's completely filled, no space is there, and there you are saying that I am going to install a DC fast charging. You will not get a land sufficient amount of space to install that. So in that case, because sufficient amount of space means, if it is low frequency transformer based solution, then it is the converter size, the low frequency transformer is bulkier, heavier, and it takes lot of space to install. Instead of that, what we can do is we can use a high frequency transformer based solution. If it is a high frequency transformer based solution, the size of the solution, the size of this complete solution becomes smaller, and you can install easily. There are certain demerits there as well, but I'm saying that if it is a space is a constraint, then you can go for high frequency transformer based solution. Now when it is renewable, now let's say we were talking about that EV success is not there if we don't use renewables. Okay, fine, grid is there, then you integrate the renewables. So renewables means PV, wind, and then you need energy storage, because PV, wind are intermittent in nature. It is not constant throughout the day. There is a variation in solar irradiance, variation in solar power generation. So in order to cater that, we definitely need energy storage. And then you have a AC bus, and then you have multiple power converters. You need multiple power converters to integrate those with the grid. So here one thing we must mention, that there are two things that is very very important for this technology to develop. One is power electronics, another one is control of the power electronics. Okay, these are the solution point of view. This is solution point of view. Here also power electronics is there. Huge amount of power electronics involved in electric vehicle as well. Okay, and then there is an improvement in PV system. PV system means solar cell. We can improve the solar cell technology and all. That is another aspect. Here also, here what we have is, we have DC grid. Here we have DC bus. Here we have AC bus. Here we have DC bus. So both the solutions are possible, and here using this converters and renewables and grid, we are providing power to charge the electric vehicle. Now let's see what are the different charging power levels. Why I am giving introduction to all these things, because this will give rise to the problem that we are facing, the challenges that we are facing, and then we'll see how machine learning can help us to mitigate these challenges. Okay, so now there are three charging options: level 1, level 2, and level 3. This we are not talking about this. We are talking about this level 1 and level 2. Let's say first. So level 1 is nothing but the home charger that we have with the electric vehicle. The electric vehicle, when you are buying a vehicle, they will provide a charger, which charger you are going to use at home, and using that at low charging current level, at low charging power level, you are charging the vehicle, and that is why it is going to take huge amount of time to charge the electric vehicle. In contrast to this, in level 3 is DC fast charging. You see the power level. This is old though, in 2013. So this is the power level. Okay, and it takes around much less amount of time it is going to take from level 1. So this is outdoor charging. Outdoor charging means there is a charging station, and there I have seen there is a parking lot. In that parking lot there is a charging facilities available. Bharat DC fast charger. Okay, that is available. And yes, there are cars which are parked there and charging from that is called public charging station, or that is called DC fast charging. Since it is DC fast already mentioned, so DC fast charging facilities available. When it is public charging station, the space is not constrained compared to the home charging, where the space is a constraint, because you cannot install a large charging solution at home. Okay, now let's see how the different companies are going to provide. Companies are going to provide the DC fast charging power level, DC fast charging power. So here you see ABB is providing DC fast charging 350 kilowatt. Links are here. Okay, links are here. If I click, it will go to it. But to save the time, I am not going. But there is not huge difference. So here, this you see here, the charging power level is 350 kilowatt. This amount of power, and see it is taking from utility grid, 400 volt AC plus minus 10%. Here Tesla supercharger is there. Now it is more than 135 kilowatt. You can see over internet. And here also it is taking from conventional utility grid. Here also it is taking from conventional utility grid. The charging power level now crossing, touching 500 kilowatt, and the utility grid has to supply. Fine, utility grid will take care. Okay, utility grid will supply, but utility grid need to know when to supply, and how much to supply. Those things, if they know beforehand, let's say it's like there is a surprise test and there is a schedule test. Okay, so people always, students always complain about they don't prefer surprise test because they are not prepared for it. Here also, grid will not be happy if you surprise grid with this amount of power suddenly. So if grid know that okay, we have to supply this amount of power at this time, it's fine. They will take care of it. Okay. Now, this uncoordinated charging scheme. What is it? Now, let's say there are electric vehicle, there is a charging station, and that charging power is taken as I have shown you. So, power grid and then renewables, and there is no coordination between these. Fine, that's fine. That's fine in the sense when the number of electric vehicle is less. Okay, grid is huge. Now, India is one nation, one grid. The entire India is now connected. Previously it was, there was five regions, east, west, north, south, and northeast, and there was connection between these regions through HVDC grid or HVDC grid. Now what they did is the entire India grid is one grid, so you never know from where the power is coming. Okay, if you let's say you are sitting in Rourkela, and maybe it might happen that the power is coming from Kolkata, maybe power is coming from Kolkata, you never know. And then when it is entire grid, when it is uh, a huge grid, that means inertia of the grid is huge. What is inertia? That means you have a big rock, and when you are pushing it, the change in state of the rock is not significant. Here also, when the grid is huge, the inertia of the grid is huge, whether you are taking this amount of power from the grid is not going to affect the grid frequency. When you are taking active power from the grid, it is adversely affect the grid frequency. Okay, it is connected. This statement is connected with the synchronous generators which are generating power at the generating station, because it has to supply the, because steam eventually, the if it is a coal based power plant, the coal is burning, it is producing steam, the steam is running the turbine, the turbine is connected with the coupled with the steam coupled with the synchronous generator, and the synchronous generator rotor actually eventually going to affect. Okay, so that is why when there is an active power consumption from the grid, electric vehicle charging means they are going to take active power. I will talk about this active power. So it is going to affect the grid frequency. Okay, so if it is this amount of this electric vehicle amount is not significant, then it is not going to affect the grid frequency significantly. Now, I always talk about active power, active power. When we are charging the vehicle, the active power is consumed by the battery. Now, it is mandatory that charger that you have built, that charger has to take only active power from the grid, only active power from the grid, not reactive power. Because you must be knowing, if you studied electrical engineering, you must be knowing there are various negative effects of consuming reactive power from the grid, because without reactive power you cannot run any equipment. Okay, but the advantage of reactive power is the reactive power you can generate locally. So grid is saying that okay, what you do is you don't consume it from the grid, you consume it locally. Whatever amount of reactive power that you need, you generate on your own, and you just take active power from the grid. Reactive power is generate on your own and take active power from the grid. So that is why now it is mandatory that converters of a certain power level, you have to take only active power from the grid. That is why I am talking about that active power. When it is EV charging, it is going to take active power from the grid, and when it is taking active power from the grid, it is going to affect the grid frequency. Now, when there is no coordination, you can see here, this was the residential load, the blue one. When it is EV is coming into picture, you see here, night 8 p.m. there is a there is a shift of the peak load on the grid. it was previously it was 0.8, now it is almost touching 1. So there is a significant increase in power consumption from the grid. This will here the grid may face challenges. Why I am talking about this? Now let's say the summer season. Okay, so now summer is unbearable. Now almost who can afford, now everyone is buying AC. Who can afford, they are buying two ACs. Okay, but the thing is they are buying it, but grid has to supply that power. Now when it is hot summer, and during this time almost not significant amount of houses are homes using AC, and on top of it you are putting this EV load. Now let's say it is this peak is because of AC, the peak is now here, and again you have to cater this load. Now you will cross this 1 pu, then it's a significant adverse effect on the grid. So there is, so what the grid has to do, the only possibility that grid has to do is, in order to save, in order to maintain the stability, it will start load shedding. Okay, so certain area they will cut out because they are unable to cater the load, and it has to run. So they will do the load shedding. Okay, they will load shedding, and they try to save the grid. Okay, so what are the grid connected EV chargers? When it is grid connected EV charger, what are the adverse effect? So voltage stability, frequency stability, rotor angle stability. Now, what are the solutions that we can implement? So V2G means vehicle to grid. Okay, so for stability purpose, vehicle to grid is going to help us, because now it is like vehicle, or you forget about vehicle. It's nothing but we can see it as a battery. Okay, energy storage. The vehicle can be seen as an energy storage device. So when there is a stability issue in the grid, it is possible that vehicle operation we start, and we can supply active power to the grid from the vehicle, but the user is not. Hello, hello, can you
Hello,
hear me?
sir. Yeah, yes, sir.
Can you hear? Actually, this tab is connected with the mobile, and I got a call on that mobile, and it got disconnected. Okay,
Okay,
now
sir.
I was here. So now vehicle to grid system, when it is vehicle to grid, let's say you are the owner. So when your battery, let's say you charge the vehicle, let's say you charge the vehicle, and your vehicle is in your garage peacefully residing. Now the vehicle to grid operation initiated. Now vehicle will start supplying power to the grid. There are two effects. One is your vehicle battery is SOC is going down. That is one thing, fine. But if it involves this vehicle to grid operation, involves your battery, so your battery is engaged. That means you are using the battery continuously. That means it is affecting the battery state of health of the battery. It is affecting the state of health of the battery. So the user may not agree with this, because it is deteriorating the battery life. So vehicle to grid may not be feasible in such scenario. Optimization of EV charging scheduling, that we'll see. Implementation of smart charging. Smart charging is like, okay, I will talk about this. And implementation of accurate load model. Okay, so when the load is coming and all that we can. Now frequency stability, so that is implementing vehicle to grid system or optimization charging control strategies. Okay, so So it's like this since electric vehicle charging is going to affect the grid, so definitely what we do is, let's talk about the charging optimization. How to optimize the charging. We will satisfy both the grid as well as the owner. Now there is a coordinated charging, there is an information flow. You can see here the green line is the information flow. Now this system operator or supervisor comes into picture, and there is a coordination between everything. Previously it was uncoordinated, and now there is a coordination, there is an information flow. Okay, now grid is overloaded, don't do it. Now grid will be not be overloaded during this time, you charge that time. So those information and optimization will go, and you can see here the peak overload has reduced and it is shifted and distributed throughout the day. So 0 to 24, the EV load is completely distributed over the 24 hours. So this is how if we optimize and if we distribute the charging pattern, then the peak, whatever peak overloading where, hello, hello,
Hello, sir.
uh, is audible?
Yes, sir.
Okay, so we are saving here. Okay, so I'm skipping this now. So let's start with this. So problem. So this is part one is done. So part one, what we understood is what is EV charging, what is different charging levels, and how this different EV charging, especially the DC fast charging, where the significant amount of significant charging power is involved. There is a shift of peak overload. So therefore we need to do something in order to distribute it or in order to forecast it. So electric vehicle charging, machine learning, charging large number of EV causes substantial stress on distribution grid. We are mentioning the distribution grid we are talking about. Load curve moves upward, increase load on transformer. That is what I already mentioned. This I forget to mention on transformer. I was attending a meeting that time. A person from industry specifically mentioned that you people talk about injecting power from renewables to the grid, injecting power from several sources, injecting to the grid. You never thought about the transformers that we have installed, and transformer has to cater that amount of power. When transformer is scattering that amount of power, transformer is already bottleneck, it is already running at full load, and then you are again overloading it. You need to think about these transformers as well, because this yesterday my father called me that we have a distribution transformer very near to our home, and it is getting tripped several times. Last week also it has happened, yesterday it also happened. Yesterday they tried to rectify it, it was tripping like anything. So the transformer, if transformer is getting tripped, you are not going to get the power. That is the major issue. So you take care of the transformer as well. Intelligent and effective charge management is needed. Okay, as I was mentioning this. So grid requirement and negative effect of charging on grid needs to be considered and addressed. It has to be addressed, such as uncoordinated charging on distributor. This just just put a charger, bring the electric vehicle, charge it. It is going to affect the grid. If it is a weak grid, it is further going to affect it, because nowadays it is told that this Indian oil filling stations will be equipped with charging stations as well, EV charging facility as well. So if that is the case, fine, but you have to take care of the grid scenario at that location, particularly at that location. If that grid is capable enough to cater that thing, it's fine. Otherwise, you have to check a suitable location where you can install it. Use of RE can mitigate to some extent. Problems still occur when no proper regulation of power takes place. So RE, you can, yes, we are moving towards RE. Okay. Now V2 grid technology can also mitigate the issue and helps improve efficiency, stability, and grid reliability. Okay, it's nothing. You forget about vehicle or something. It is like you have a battery and you are supplying active power to the grid. It will help. regulate power, load balancing, current harmonic filtering. Then V2G technology cause deep discharging, battery degradation, battery lifetime, and decrease customer satisfaction, as I was mentioning. So use of intelligent charging strategies, intelligent, how to make it intelligent, that machine learning can implement it, and coordinated charging. These two we should implement, since number of EVs are increasing day by day. In machine learning, what we do is we train a computer. Okay, we have a data set. Okay, we data set a human being. Okay, if it is a small amount of data set, if we are very good in maths, we can figure out what is the pattern. If we have a huge number of data set, then it is very difficult for an human job to identify what is the pattern of the data set. For that, what we do is we use machine learning and algorithm to find out what is the data pattern, and we train the machine and train the computer with that, so that the future trend and predictions can be done. That is why machine learning come into picture. A successfully trained system able to make accurate prediction and predictive analysis. As I was telling you, the forecasting can be done. It can be categorized into supervised and unsupervised. Supervised learning use labeled data set. Okay, and unsupervised without any labeling data, raw data that you can use. So labeling of data set is time consuming and it is costly. But so let's start with the supervised. We'll see what are the different techniques that we can employ for supervised learning. Okay. So it can be based on variable to be predicted, response variable, which is called response variable. Based on that also it can be categorized into regression problem and classification problem. So we'll talk about classification problem, where we can classify the data set into maybe two or three two classifications or categories. Okay, let's see what is what is the difference between regression problem and what is the classification problem, that we'll see. So here we have taken two examples. Okay, one is the battery is charging and it is consuming power from the source, and the duration of charging, this first case, duration of charging. So battery SOC is increasing and it is consuming power. So this is continuous. So that is why it is regression problem. So energy is the response variable is energy, and it is consumed energy, and it is continuous. And distincts of two owners. Here we have two owners. One preferred to charge his vehicle, his or her vehicle in daytime. Another maybe prefer to charge his or her vehicle night time. So there is a classification. There is a distinction between these two classifications, that we'll see how it can be done. Okay. So supervised learning, so model trained from labeled data set to predict outcomes. Okay. So when you are going to implement this for EV charging, so what could be the different the data set might contain? You might have arrival time, which is input variable. Actually, let's say EV owner is coming into a charging station, and our objective is to calculate or predict the departure time, at what time he or she can go away with charging of the vehicle. Okay, so input is what? Arrival time. Location of the input variable, location of the charging station, which is input variable, and the departure time. Departure time is the response of target variable. Okay, there could be many more parameters. Just I am giving two example input variables. One is the target variable. Okay, train to learn. So it will train to learn the relationship between input variable and the response variable. So if we input these two, then the system calculate calculate from the trend. Its system is already trained. Okay, it already know what is the pattern, how the pattern goes. Definitely there will be an error. If error is within some tolerance limit, then with that algorithm it can predict at what time he or she may go from this, from after charging from this charging station. Now let's see few machine learning algorithm. One is very simple one is the linear regression, where y is the response variable and then we have inputs. So you calculate the different coefficient by minimization of sum square error. So error minimization technique that you use, and based on that you calculate the different variables, different coefficients. Then if this function is known to you, then if you give the input, those two inputs. So in previous case only this is the, in previous case only, let's say this is the equation. So you calculate b1 and b2, b0, b1, b2, and if you give this x1 and x2, it can calculate what would be the departure time. So then here what we have is if it is a linearly separable data set, if it is a classification type of problem, if there should be so there is a line, there is a separator function. Separator function is given by this fx equals to this. So on separator function, if x1 x2 is on the separator function, which is very obvious. If it is a separator function, if it is this data set on the separator function, then this separator function will become 0 at this separator line. So on when it is on the other side, fx greater than 0 on one side, fx less than 0 on other side. So if you know the separator function, then based on that you can classify the data set, and the data set should be a linearly separable data set. So here you can see it is not linearly separable data set. It is not feasible to separate out the or classify between the two sets of data. Now the problem is, if you have outliers, you cannot fit this into the data set. This is the problem. Then we have decision tree. Decision tree is nothing but it is similar to a flow chart. Let's say how it works for, let's say for electric vehicle charging. So we start with this. Acha, first explain this. So complex decision. Okay. So complex decision, combination of simpler decisions. So it takes simpler decision in step by step, and then you find out what is the decision. The split points from the input features, decision points are decision node, and no further split, then it is leaf node. That is why it is green color, no split points. And this is decision node. These are decision nodes. Okay. Now let's take one example. Now you are checking SOC is less than 60%. If it is no, then no charging is required. If SOC is less than 60%, yes, slow charging station, the charging station is slow charging station, yes, I'm not going to charge there. If it is no, check whether it is waiting period is long or not. Yes, no charging. If it is no, then you go for charging. So decision tree is this one. Should I charge my EV? So based on this decision, you can you need to charge from this particular charging station or not. That can be decided. But the problem is when it is a single decision tree. Often it fails in good predictions. Okay, so very obvious, if it is fails for prediction, then what we do, we take multiple decision trees. When there are multiple trees, it's nothing but a forest. So that is why it comes to random forest. So here we have multiple decision trees, and then we average, and then we do the averaging, and then we do the prediction. Okay, so predictions by aggregating multiple decision trees. Okay, one decision tree may be wrong. So that's why what we do is, when we diagnose with something from one doctor, what we go for another opinion, right? Second opinion we go for it. Why we go for it? We check whether this is matching with the previous doctor's decision or not, and this is how we take the decision. Here also the same thing is happening. The model one, different models are there, different data sets are there. Based on that, we take one decision, another decision from another decision tree, and then finally we'll average and predict it. So regression is done by average predictions, classification by major vote across the trees. So it is like multiple experts and opinion, and then voting to make the final decision. This is the difference between random forest and decision tree. Now comes to support vector machine. Okay, support vector machine is also for classification problem. Okay, now this support this I will not go further into mathematics into it, but I will show you one case study, one paper presented how support vector machine can be used to predict the load forecasting. That is there in that paper. I will show you how they have predicted it. Load forecasting they have predicted, and they have compared it with Monte Carlo technique, and they they concluded that they are predicting for short term load prediction. Short term means from 1 hour to 1 week load prediction. This support vector machine is predicting better than the Monte Carlo technique. So here what we have is, we have two classes of data. No, okay. Now what we classify into, so there could be multiple classification lines. So that multiple classification line, the multiple classification line, we can classify into two data sets. So multiple classification lines makes you the hyperplane. It's a plane, multiple lines, it will make a plane. Now there will be a boundary to that plane. So one boundary is negative hyperplane, another one is positive hyperplane, and there is a middle line which is maximum margin. What is margin? The margin is, sorry, that is maximum margin hyperplane, the middle one. Maximum, that is one negative hyperplane, positive hyperplane, and that is maximum margin hyperplane. And this is the maximum margin. The distance between these two is maximum margin. Now how to decide on maximum margin? There are support vectors. You can see here one support vector here, another support vector here. This support vector defines the hyperplane, the border of the hyperplane. The support vectors are the extreme points. Extreme point means, let's say give one example. There are a mix of cats and dogs. Okay, now you separate out, these are the cats, these are the dogs. Now there are cases, extreme cases. Let's say there is an example where we have a cat whose characteristics is, some characteristics from the dog is available as well. Okay, so those are the extreme cases and will lie around this hyperplane, the margin of the hyperplane. Okay, so those are called the support vectors, the extreme cases. So hyperplane, multiple line decision boundaries to segregate the classes in n-dimensional space. It could be 2-dimensional, it could be 3-dimensional. Okay, this enough literature is available. Now hyperplane is always the maximum. Hyperplane always have the maximum margin. This is the maximum margin. So hyperplane, between the distance between the hyperplanes, positive and negative hyperplane, is the maximum margin. So closest data point to hyperplane determine the support vector, as I was explaining. Okay, so large training time not suitable for large data. So if it is large data set, so training the system becomes time consuming. Then we have k nearest neighbor. It is very basic and essential machine learning algorithm for classification problem. It's a very simple actually. What we do is, first let's understand these two are the data sets. These two are the data set, and this is the new data. The black one is new data, and this data is not used in the classification. Is not used for this training purpose. So it may act as an outlier. So we have a data set 1, data set 2, and then we have a new data set. So what we do is, we check the nearest neighbor. We check the nearest neighbor to this data, nearest neighbors to this data. So Euclidean distance, nothing but the distance between this point and the neighbors. The distance, Cartesian distance, that we calculate, and we check the shortest distance, and those distance we consider. So it is given here. So target point is here, and these are the two data sets. These are the two classified data. Now class 1 and class 2. Now they are calculating Cartesian distance between this class and this class, and then they define on which class it is the shortest distance. The data which is having shortest distance to the class, it will belong to that data set. So here is the distance. So calculate the distance and check which is the shortest distance and where we have the maximum number of shortest distance neighbors, and the data will belong to that data set. This is how the k nearest number k nearest neighbor algorithm works. Now these are the supervised learning these are the supervised learning machine learning algorithm. Now what we have is unsupervised learning. Unsupervised learning don't use labeled dataset, so comprised only input variables without labeled output variables. So data labeling is time consuming and costly. This is to find the structure or pattern within the dataset. So items have, okay. Now here you can see here we have three clusters of data. Okay, so how they are charging. So EV charging, how they are charging. So arrival time, departure time. So this is defined during weekdays when they are coming and when they are departing. So cluster 1, they are coming on weekdays. So if 1, 2, 3, 4, 5, 6, 7, if you do, so on which day they are coming and what is the departure time. On which day they are coming and what is the arrival and departure time. Okay, this is how. So this is how you can calculate, classify the different cluster, the data into different clusters, and you can calculate what is the departure, arrival and departure time you can calculate from this. So therefore the researchers are looking for EV to be charged smartly. So EV to be charged smartly means it involves both. One is the source from where it is charged, and the EV also. EV also means you as an owner should be able to know. I am giving you one example. Let's say you are an EV owner, and let's say you have an app. Okay, in that app it will show you what are the charging locations available at your current, near to your current location, and what is the departure, what would be the departure time if you go at this time to that charging location, and what would be the cost benefit. Let's say you have a nearest EV charging station, but if you go there, so since let's say you are an EV owner, you are at a certain location. Now you are looking for EV charging, you are looking for charging station. Now you got, let's say, three charging locations. One is nearest to you, another one is a little far, another one is farthest. Now definitely we'll go to the nearest station. Now you check the queue that you have to the queue. What is the status of queue in these charging locations? Now you have seen that the nearest charging location is having less queue, so it is favorable for you. You will go to that charging location. Now the problem is, let's say that charging location cannot cater huge amount of EV chargers, a huge amount of electric vehicle to charge. So in that case, what you are going to, the customer should get is cost intensive incentive, so that customer will not go to that charging location, it will go to other charging location. Let's say if you are going to this nearest charging location, the cost of charging will be high, but if you go to, let's say, nearest second nearest charging location, the tariff will be less there. So definitely you will change your mind and you will go to that second nearest charging location. This is how it is going to help you in both the way. One way is it is helping the customer, also it is helping the grid as well. So cost benefit should be there to choose the customer which charging location he or she must go, and also the information should be available, could be available with the EV owner, so that he or she can charge his vehicle smartly. That is why EV to be charged smartly from both the ways, from utility point of view and from the customer point of view. That is why cheaply, if why efficiently, I will tell you cleanly. And so efficiently, what is the meaning of efficiently? Now let's say that app will tell you that there are, as I mentioned, that level 1, level 2 and level 3 charging facilities are there. When it is outside, it is not level 1, it is either level 2 which is, and level 3. Level 3 is DC fast charging. Another one is level 2, which is comparatively slow charger than DC fast charging, but significantly high charging rate compared to home charger. Now, when a customer is going to a charging location, it has to decide whether this EV should be charged from level 3 or level 2. That information should be decided by that app, because the EV owner may be a layman. So so if you do that, if that app is going to do that, that charging will be efficient, and also that charging will be efficient from the customer point of view as well as grid point of view. That is why it is mentioned efficiently. This is what from grid, which may not be able to accommodate all EVs at a time, as I was mentioning. Charging station makes trade-off to make each car being charged efficiently, as I was telling you, level 2 or level 3. So this is how you see here the problem was how to charge the EVs, DC fast charging, or how to accommodate the EV charging to the charging station where significant amount of charging power is being taken away. Okay, so in machine learning, what we do is we train the model using constraint and schedule charging time within peak demand of the grid. We are taking care of the peak demand of the grid, and accordingly we are scheduling the charging. That is how the distribution of the load is happening, as it was previously when it was happening at the peak of the grid power. Now it is scheduling the charging so that it distributed over the 24 hours. Multiple EVs charging at the same time creates peak overload demand, as we already mentioned. So based on this data, scheduling algorithm become more efficient and intelligent. So it is intelligent to accommodate the charging of an EV. So smart charge scheduling is to optimize charging, allows network charging station. So now, as I was talking about the app, so app will be connected with the charging station. It will be connecting to the charging station with the customer. The customer will now be able to connect with those charging station, as I was giving you the example of charging station 1, charging station 2 and charging station 3. Also what it is doing is, it is when you are going to that, so you made your mind and you went to some charging location. Let's say you are not bothered about cost, you go to charging station 1. Okay, you bothered about the cost and you went to charging station 2. So the app will store the data. So what was the behavioral pattern, and also it will store how what is the arrival time, what is the departure time, what was the SOC of the state of charge of the battery, what was what was the which charging level was selected. Those data it will store and further improve the model. So charge management and charge scheduling of EV is required, and that is done by machine learning. Machine learning may be used to route EVs to charging load variance. This I already mentioned, but I am again explaining. So as it is routing the EV owner to a specific charging location in order to minimize the load variation, power loss and voltage fluctuation and charging cost. It is taking care of both grid and the customer. Analyze charging data to ensure grid stability, reliability and peak and prevent overloads. Optimize charging distribution, energy distribution, allowing dynamic charging rates based on grid condition. And so whether it is level 2, level 1 or level 2 or level 3, it will decide based on grid conditions, energy demand and all. How much time you have. If you say that I have 1 hour, okay, go for level 2, let's say. Fostering grid sustainability, it is helping the grid. Okay, grid got some respite. Driving V2G integration. If customer is satisfied in the charging location you are charging, if customer is agreed, then you can go for it as well. Reduce carbon emission and contribute to sustainable energy system. And machine learning to optimize charging at suitable charging station with suitable charging speed, as I already mentioned. This thing I already mentioned. Okay. Achha, machine learning parameter. This I will come. Before this, I want to know how much time I have.
Sir, nearly 15 minutes. 15.
Okay. Okay, 15 minutes I have. Okay, so okay, it is already 11. So Okay, there are papers, various papers are available. Just I want to give you, can you see this paper?
Yes, sir.
Okay, forecasting electric vehicle charging demand using support vector machine. Okay, so it is saying support vector machine, but it could be any machine learning algorithm. Now it is your judgment which machine learning algorithm is going to give you the best result. So here the authors has taken support vector machine and they compared it with the this with the Monte Carlo technique. Okay, now what that, so this paper proposes a short-term load forecasting. Short-term load forecasting, what they are mean for this is, so here you can see, so short-term load forecasting, here you can see short-term load forecasting here for forecasting is used to predict the load demand, okay, from 1 hour to 1 week. So if that forecasting is available with the utility company, it becomes easier for them to be prepared for this. Okay, so 1 hour is sufficient enough. They can prepare themselves and they can supply that amount of load. So it plays, you see here what it says, that as I already mentioned, that it plays a significant role for the next day unit commitment and the optimization of grid operation. So if we know that, okay, this amount of load I have to supply, so we are ready, and we are ready with the grid optimization operation, grid stable operation as well. Here they are giving, they have cited one, what they are saying is, and 1% reduction in average forecast error can save 10 million pounds from operating cost in the UK power system. You can see how significant it is. Okay, so that is why this forecasting is going to help us. Forecasting is going to help us in EV charge EV charge scheduling. Now you see here, so how it works. So this is the flow chart. So first you need, what you need is historical data. First you need historical data is the input. Then you have to format that data suitable for support vector machine algorithm. Then define the machine parameters, then the training process, then you cross validate, and then train the model. These are the steps that you have to follow. Okay, so first historic data you must have, then you do the data formatting suitable for SVM, and then define system SVM parameters and SVM training process initiated, then cross validate and train the model. Now model is ready. Now new data set is coming. New data set is coming, and based on that you have to forecast. So SVM forecasting and final forecasting will be done. So then first thing what you need is historic data. So how to get historic data? Okay, now here they are starting with historic data for 365 days and for n number of electric vehicle. Okay, so now they are first started with day 1 and vehicle 1. Select the vehicle class, what kind of vehicle it is. So what is vehicle class? They have mentioned what are the vehicle class. These are the vehicle categories. Okay, so small EVs, then passenger vehicles, and then goods carrying, and then goods carrying with higher load. These are the classification they have done. Then driving pattern. What is the driving pattern? You need to know what is the driving pattern. The driving pattern is given here. This traffic distribution driving pattern, I think it is not given. Driving pattern. Okay, so you have to fit the driving pattern. Then travel distance, arrival time. Those things are available from here. The travel distance, average distance travel daily. Okay, that is given. Probability. Probability. What is the probability of travel distance travel distance in percentage is given, and also the arrival time. Here the traffic distribution and arrival time, they have, this dotted line is the arrival time, that is the 30 minutes delay they have taken, and based on that they have plotted the arrival time distribution curve as well. So you can get the arrival time as well. Then we do the calculations. Then they can calculate the how much energy is needed, what is the charging period, and update the daily charging demand table. When it is 1, it is starting, and then for different n, it will keep on updating the table, and then it will update for 365 days. It will do, and then the historic data will be populated. When you get the historic data, then you can employ it for SVM. So here is the historic data that we need. That data is now available with you. Use this for SVM, then you can get the forecasting load. So they have done it, and what they have presented here is, here is the forecasting. So you can see here actual. Okay, so this is charging demand, y-axis is charging demand, and this is the time of the day. Okay, so 24-hour, how is the charging pattern? So here you can see that dotted line is the actual charging demand, and the red one is the forecasting. Okay, so it is matching, and it is not that absolute matching. They have calculated, they have taken some error, root mean square error, and two errors they have considered here. One is mean absolute percentage error, and root mean square error. These errors they have considered, and that error they have mentioned there, how much error they have, that I will show you. So this is how the prediction is done for charging demand, and then they have compared it with okay, they are with Monte Carlo method. You can see here with Monte Carlo method. Here you have, you can see here the load pattern, the charging demand in kilowatt. You see here the dotted line is the actual one, and with the Monte Carlo it is the green one. So they concluding that with the Monte Carlo, with the support vector machine, it is comparatively more accurate than the Monte Carlo method. But the thing is, there are other machine learning algorithm which you can employ and check whether whether which one is going to give you better accuracy, which one is going to, not only Monte Carlo. There are other methods that you can employ, and they are saying here, you see here the performance measures they have taken. So mean absolute percentage error, SBM is giving 3.69, whereas Monte Carlo is giving 8.99, and root mean square error, it is 50.13. Here it is 105. So definitely compared to Monte Carlo, they are showing that the load forecasting, what they are doing with SVM, is comparatively accurate than Monte Carlo method. Okay, so this is how you can employ machine learning algorithm for load forecasting. Okay, there are papers on, there are work on this SOC estimation of the battery as well, state of health of the battery, and other things are definitely there. So what we can do is this machine learning. Now this EV charge scheduling is very popular using machine learning algorithm, and using machine learning algorithm, and it is being in near future it will be using rigorously, because the huge amount of data, it is only machine learning can derive the pattern, and based on that forecasting can be done. Okay, so since time is almost over, so just limitations are there. Just let me explain the few key limitations. So algorithm run accuracy may fluctuate and cannot predict with the high precision. Okay, high precision is needed. You forecasted something and actually something, then you will fail while actually meeting the load demand. Algorithm runs multiple times and validated to ensure high accuracy with small standard deviation. That you have to ensure. The accuracy of dataset used to train model effectively. Dataset should be large. Small dataset will give you erroneous forecasting. Okay. So conclusion is EV charge scheduling can use machine learning as an optimization technique to minimize the load variance, power loss, and voltage fluctuation. So machine learning, we have to meet EV charging demand, and we have to supply from the grid. So machine learning is going to help us to save both grid as well as the EV charging owner as well. As a result, power overloads in the transformer do not occur, which decrease power outages, as I already mentioned. In addition, the decreased power loss and voltage fluctuation increase power quality of the distribution network. Further, user satisfy is considered to minimize the charging cost, as I was telling you. Okay, few references, and I'm stopping here. Thank you. So, if any
Thank you, sir.
questions.
Thank you, sir. Thank you so much for sharing your valuable knowledge, sir, in the field of electric vehicle.
Mhm.
We hope this will be really helpful for all the participants.
Mhm.
Now I am requesting every participants, please, if you have any question, you can raise your hands. Participants, please turn on your mic and ask the questions.
Hello, sir. Am I audible, sir?
Yes, yes, you are audible.
Sir, firstly, thank you so much for your presentation, sir. Actually, sir, please explain first, sir, the method of Monte Carlo simulation. Actually, sir, I didn't get it, sir. Kindly, sir, explain how Monte Carlo simulation work. And sir, second question is that, like other methods, other model-based methods like particle filters and Monte Carlo, how, sir, SVM, because particle filters are based on stochastic-based statistics, like SVR also works on that field. So means particle filters also means great algorithm. So means how SVM can different from that kind of thing, sir.
Okay, so this a generic question. Everybody, this question will come to many of you, because as I was mentioning, it is we are interested on, as an electrical engineer, we are interested on the forecasting, how forecasting is accurate. Now that forecasting could be accurate with any of the machine learning technique, and also can be accurate with the Monte Carlo at certain assumptions and all. Now how that is going to give you accurate result, that is the mathematics behind that particular machine learning algorithm. But your job is to find out which method is going to give you the best result, and which method is going to give you the accurate predictions compared to other. Now how that mathematics is going to work, that you have to check. That this, because of this is the research work, that this method is giving me the accurate. Here they have mentioned that compared to Monte Carlo, this SVM is going to give us the better result. Now your job is to find out what mathematics difference is coming into picture. Because of that, these predictions are getting more accurate in case of SVM compared to Monte Carlo. It might happen that whatever we are expecting for a particular scenario may not be accurate for other scenario. That you have to take care of it. That you have to look into it, and you have to find out which is best, and based on means best and why it is best. That mathematics that you have to look into.
Thank you, sir.
Indrajit sir, since we are running short of our schedule, so at this point of time, we will not be accepting any further question from the audience.
That's fine.
If any query you have, you can be able to contact with Professor Indrajit Sarkar through email and all. So the feedback form is already shared into your chat box. So kindly just fill this up for this session. And yeah, here at the end of this session, we would like to thank Professor Indrajit Sarkar for his extensive expertise that has been shared with all the audience present over here. And as a customary, we will be having a group photograph at the end of each of the sessions. So I'll be requesting Professor Sarkar and all other participants who can be able to turn on their camera. So this memory can be captured over here with us. Professor Sarkar, kindly stop your sharing so the screen can be properly visible. Yeah, thank you.
Okay, sir. It is up. Now we can turn off your camera. Okay.
So our second session speaker has already joined with us. So we will So at this point of time, since the speaker has already joined 15 minutes back, so we will not be spoiling much of his time. And we will take a short break over here. Within 5 minutes, we'll be starting our next session.